Okay, so welcome to the afternoon session of day one of this RL workshop. It's a great pleasure to have Professor Shai Manor with us. Professor Manor is the incumbent Edwards Chair in Engineering at the Electrical and Computer Engineering Department at the Technan. He has published over 80 journal papers and over 250 conference papers, and his papers were cited over 32,000 times with an H index of 90. Professor Manor's research interests include machine learning and data science, with an emphasis on reinforcement learning, planning and control, and analysis and control of large-scale systems. He has co-founded 4 companies, and currently he's a distinguished scientist at NVIDIA. Okay, so with that, we're really excited for your talk.
Thank you for the invitation. I think you should see my slides now. Can you see them? Okay. Thank you. Thank you for the invitation, and I decided to take this opportunity to tell you about 2 research directions I've been working on in the last few years. And this is sort of an incomplete story. So it's a tale of 2 research problems, which I believe are the same problem, but we'll get to it, and I think you'll see why the story is incomplete. And if somebody here in the audience knows how to complete it, that would be great, because it's a daunting effort to try and make the story complete. So I'll tell you today about robust MDPs, which is something I've worked on for several years, and also about delayed MDPs. And basically, I think what we'll see that those are 2 fairly different problems, but maybe they're really telling the same story. So let me start with some introduction and background on MDP. So I think I don't need to say much about the problems here. Hold on. Do you see now the next slide? Because for some reason. Do you see a slide? Okay. So let me.
We can see the second slide now.
Yeah. Okay. Okay, we'll just do it like that, if that's okay. So I'll tell you about the setting that I think is really familiar. It's not about the fancy setting here. It's really about the fundamentals. So we'll talk about the simple, discrete decision epochs, finite state and actions. So S is states, A is actions. We assume that there is a transition kernel from states to the next state, and the reward is going to be deterministic throughout this talk. So the setting is the simplest, most vanilla setting of all. I mean, like in most RL MDPs in RL work, we'll talk about trying to optimize the policy rule based on history. So history here is H of t. It's a sequence of state actions and from time 0 until time t. That's our history, and we're looking for a decision rule, which in general is history dependent and stochastic. So that's to remind you the general picture. There are history-dependent policies, random and deterministic. HR is this history-dependent and random. HD is the history-dependent and deterministic. And then within the set, there is a set of Markov policies, which is a policy that only depend on the current state and not on all of histories. Again, random and deterministic. And of course, our favorites, stationary policies. Those are policies that only depend on state and do not depend on time. And usually, in most of MDP literature, we're pretty pleased that we can have a policy which is optimal and stationary and deterministic. So those are. This is a sort of a very quick overview of classical results in MDPs. Okay. So the optimization problem that we'll deal with is we'll look for the optimal policy. So a policy can, in principle, depend on time. If it's stationary, it does not depend on time. And our objective is to maximize the expected cumulative discounted return for a given policy policy pi. And do note that we have here a subscript P and R denoting the dynamics and the reward. So this is for a certain transition dynamics and for a certain reward function. And the objective is to maximize either the Q function of pi, so basically to find a pi that maximizes for every S Q pi of S and A, or alternatively, if the model is known, just to find the value function, which will sometimes denote by this inner product between a policy and the Q function. This is sort of the value a notation for the value function, and we'll by and large this is sort of the simple setup of optimization. There is nothing fancy here so far. So we know that it's well known that in infinite horizon, the infinite horizon optimum is a stationary deterministic policy, and the finite horizon optimum is a Markov deterministic policy. There's no need for randomization in any problem which is not constrained or risk aware, and moreover, those results are I think by now pretty well established. So why do people resort to robust MDPs? That's always a question that is bothering. So there are many reasons. I'll list a few of them here. So in classical MDPs, we know that there is if the model is assumed to be known. So it may be that the model itself is not precisely known. Maybe we estimate it from data. Maybe we have some initial idea what the model should be, but maybe it changes. But in any case, in classical MDPs, one can think about it as if we have data and we have a point estimate. Maybe we want something which is a bit more like confidence intervals around it. So classical MDP, we need to assume that the model is known. That's often not the case. If the model is estimated from data, that is certainly not the case. The other aspect can be that maybe the dynamics change. So maybe the dynamics change with other time or with perturbations. So maybe my MDP is the behavior of a machine, and there are 100 machines, and every machine is a little bit different. So there is a small perturbation between the dynamics of the different machines. And then, last but not least, the dynamics may also change in an adversarial manner. And then that's something that we need to account for. So maybe even somebody is trying to maliciously attack my model. So those are not covered in classical MDPs. And the standard solution is what's known as robust MDPs. So in a robust MDP, we assume that we don't know the model parameters, and what we're trying to do is we're trying to find a policy that is good in the worst case. So to be more precise, the standard definition of robust MDP is an MDP with uncertain model parameters. So we don't have P and R anymore, which are fixed, but rather we know that P and R lie in some given uncertainty set. So we'll denote in this talk the uncertainty set by U, and we can assume that it's a product set between uncertainty in the transitions and uncertainty in the reward. Importantly, it is assumed that the uncertainty set is given, so it's prescribed as part of the problem. And in the vast majority of robust MDPs, learning of the uncertainty set is not done. So now when we turn our eyes to robust MDP, now our objective is we're looking for a policy pi. But the objective that we're trying to maximize now is going to be what's known as the robust value function. So the value function for policy pi when the uncertainty set is U is defined as the infimum. So that's the worst case transition kernel and reward function. of the value function v of pi. So here we fix p and r to be the worst model parameters for the particular pi, and basically that's we're trying to find the best worst case policy. Okay, so robust MDPs have been around, I think, for at least 20 years now, probably more. But at the model themselves, they optimize with respect to the worst case model. So it may be that the worst case model is really bad, and epistemically, from an epistemic perspective, this model, it might be the model that we specify can be quite difficult to solve. So to try and fight the over-conservativeness that is innate in such a worst-case model, there are several ideas of what has been proposed. Here are just two. One is soft robustness. So we sort of embed the model with additional probability, and we're saying that we don't want our policy to be good for the worst case, but rather to a slightly better worst case. That's one approach. The other problem, the other type of way to combat this worst case approach is to say, well, there is a really worst case, but we also know something about the actual case that we get to see. So that led to several works on latent models. In latent models, we get to see something, and we hope that it's going to give us information, but we still want to perform well in the worst case. So there are ways to remedy some of the issues with robust MDPs. Another example is that is to try to sometimes we want to have the uncertainty set not fixed. So basically, we want to learn it somehow. We want to modify it. We want to do something that could be somewhat more useful. And that again, there are some approaches how to deal with learning the uncertainty set. By and large, you need to make some assumptions on what you know and what you don't know. Here is one example, how to construct uncertainty set online. And that's something that is potentially very useful, but we're not going to talk about it today. So that's some other research which is really interesting. But today we're going to talk about something else. Today we're going to talk about the expensiveness of robust MDPs. So today we'll talk about why robust MDPs are expensive and a potential solution how to solve it. So the reason that robust MDPs are expensive are a problem is that you need to solve a max mean. So you're maximizing over the policy and you minimize it over the uncertainty set. And that's really going to be a saddle point type of optimization. And there is no reason to believe that that's going to be computationally easy. So what we're going to present today is a connection, perhaps somewhat surprising connection between regularization or regularized RL in general and robust RL. So what's regularized RL? So in regularized RL, we solve the classical non-robust problem, and then we add some notion of preference to simplicity, either simplicity in policy or simplicity in value or simplicity in something else. But regularization in general encourages simplicity. And it is regularized RL, regularized MDPs are pretty standard, I think, by now. It is known that they improve policy exploration because you tend to have simpler policy, meaning less deterministic policy. It improves stability during training because when you're doing function approximation, then your objective function is going to be something that is more that is easier to handle. And it is more computationally efficient because you're solving either something which is locally convex, or if you're fortunate, something which is actually convex. So you can compute gradients. Gradients are stable, and everything it works. However, so far it has been thought that regularized RL does not encompass any model uncertainty. And what we'll show, that's indeed true. We'll show that regularized RL indeed is not always a robust to model uncertainty, but sometimes it is. And in fact, we'll show that if you play your cards right, and if you carefully build a regularizer, then what you're really solving is a robust RL problem. About robust RL, so robust RL encompasses model uncertainty in the most obvious way. So we're actually taking everything into account, but it is thought to be computationally expensive. And what we'll show is that robust RL in general is much more expensive than regularized RL. But if you'll choose your uncertainty set wisely, then in fact your problem can become a regularized RL problem and can be solved efficiently. So we don't claim that all robust RL algorithm or formulations are regularized RL and vice versa. We just claim that some regularized RL formulations are robust RL formulations and vice versa. Okay, so what are the main contribution of this work? So the main contribution are that we show that if you're doing policy regularization, then in fact you're solving a robust MDP with uncertainty reward. This is a fairly easy case in terms of robustness, but we can show that you can derive a policy gradient theorem for a reward robust MDP. Then we show that if you have robust MDP with uncertainty reward and transition, of course everything here, there are fine prints that I'm not going to mention in this slide, but not all robust MDPs. Then this, in fact, is the same as MDPs with policy and value regularization, and we call that twice regularized MDPs. So this is the R square that you see here. It's twice regularized. We regularize the policy and the value function, and everything will flow through a new Bellman operators that are going to be contractive, and that's going to allow us basically to have a computationally efficient robust planning algorithm, and moreover, it will allow us to have an MDP and a DQN type algorithm to solve the problems. So this is an overview of the contributions, and I think if there are any questions, now would be a good time to ask them. Okay, so I will continue. Okay, so let's have a few preliminaries. So we have an MDP like we had before. So an MDP for us is state, action, discount factor, reward, and transition kernel. We start from some initial distribution, which we'll denote by mu0 throughout this talk. And the policy is really just a mixed action over tells me how to randomize actions for every state. The standard classical value function equation it's a fixed point equation where the value equals the reward plus discount factors times the transition matrix times the value function. When you want to regularize the value function, then you have to modify the reward, and the modification is what's written here. V equals the reward minus the regularizer of the policy plus gamma times the transition V. And really, it's really how to choose a regularizer. You can choose different types of regularizers, and the standard value function equation is unregularized, basically. So if you choose gamma omega to be 0, then that's going to lead to a standard value function. So when you have an uncertainty set, which is a rectangular uncertainty set, so you would take a product over all states of a state-dependent uncertainty set. So for a rectangular set, and everything I'm going to say throughout the talk today is going to be about rectangular uncertainty set. So the robust value function V is the minimum over PNR, so minimum over transition kernel and reward function of the standard value function, but of course chosen for this particular worst case PNR. So we have two types of equations here. We have the robust equation, which is written below, and the regularized equation, which is not robust at all. And also the two facts that I mentioned below, how to connect that not everything robust is regularized and vice versa. Okay, so let's start with the first classical result from Garud Iyengar's paper from 20 years ago. And this result shows that, sorry? Was there a question? So this result showed that you can, if you want to solve a robust policy, is the optimal solution of what's written here. So the value function, the robust value function, is solution of you maximize a linear program of v comma mu0 to remind you is a state distribution, subject to the value being less than the Bellman operator for all models in your class. Okay, so that's a result. Now, what we show in the first theorem here is that if you only have uncertainty in the reward, so that's written here, if your uncertainty set is a nominal transition kernel cross R0 plus some reward uncertainty set, so this is going to be per state, then the robust value function for policy pi is the optimal solution of almost what's written in Iyengar's paper, but now instead of having the minimum here, we have a regularizer for the policy. And this regularizer for the policy is going to depend, of course, on the shape of the uncertainty in the reward function. So the uncertainty in the reward function per state, that's what's written here. It's a function of the uncertainty on the reward, is going to dictate the shape of the regularizer. Okay, so you can compute it, and in fact, for different, you can get that for different uncertainty sets. So remember, the transition uncertainty is going to be always here constant, and here we have examples for different uncertainty set, and then you have different regularizers, and you compute the two. It is kind of a dual formulation, and the computation is not too interesting, so I'm not going to get into more details. But just to give you an example, if you choose an uncertainty set that is going to be an interval between the number of log the number of times that you sampled an action A and plus infinity, then the regularizer is going to be negative Shannon entropy. And there are other examples that are written here, and there are more examples in the papers. So what we see that we can have a dual formulation that takes an uncertainty set and brings us a regularizer. Okay. Now you can say, well, reward uncertainty may not be that exciting. Let's try to see what happens when we have uncertainty in both the transitions and the reward. So if your uncertainty set is a product set per state of nominal transition plus uncertainty set in a transition, cross nominal reward function plus uncertainty set in the reward function, then the robust value function pi is the optimal solution of the same linear left side, but the constraint is that the value is less than reward function. This is a sort of the standard Bellman operator. But now you have to do two things. You have to regularize, like we did before, regularize the policy, but also regularize concerning the value function. And when we write here v.pis, that's a point-by-point vector product. So this is a sigma. The sigma ps is a regularizer that depends on the transitions, but does not depend on the reward. So at this point, you can say, oh, well, that looks suspicious. Maybe it doesn't bring me much, right? Maybe that's very complicated to compute. So there is a way to compute the regularizer from the uncertainty set. And in fact, for at least very simple uncertainty sets, which are ball type uncertainties, so here the uncertainty in the transition is an L2 norm around the nominal, and it's bounded by some alpha S of P, and same for the reward. Then, in fact, you can show that the Bellman equation that you get is that you're optimizing the value function under the constraints that you get a standard Bellman constraint for the nominal, minus a regularizer for the policy times alpha S is the same alpha S that we have here. So that's the value function, the reward function regularizer, or the policy regularizer, and here we have the norm of the value. And we call that, what's written here, this is a modified Bellman operator, where we modify the operator for a given pi such that it's going to be twice regularized. We call it twice regularized, that's our square here, because we regularize both the policy, that's the norm of the policy, and the norm of the value function. So we regularize policy and value. And in principle, it's not clear why that would be solvable, but as we'll soon argue, it is in fact solvable. So let's call that, we have now the twice regularized, this omega, this is a regularizer. And what we can show is that you have now a Bellman type operator. So the Bellman operator that we have is the classical Bellman operator minus the regularizer. And if you're optimizing over policy, then it's just the optimal Bellman operator. So you can prove that you have it's a contractive operator, and in fact you have a fixed point, and that would be true for a fairly large number of uncertainty sets. So what it means is that if you use this twice regularized operator, then it's going to be contracting. So your favorite planning algorithm, whether it's value iteration or policy iteration or modified policy iteration, well, it's going to converge. So once we get a contractive operator, then we have a fixed point, and basically we can use all the math that we used to from standard MDPs. At this point, you can say, well, why are you telling us all that? So here is one example. So this is a modified policy iteration, policy evaluation, and that's for different values of m. M is the number of rollouts in the value iteration. So we see that if you just solve a vanilla MDP to compare, that's your compute. When you solve an R-square type operations from MPI or for policy evaluation, your compute is measured in it's roughly 2x or 3x what you do for a vanilla. And when you try to solve a robust optimization problem with some interior point method that is state of the art, to get between 3 to 5 order of magnitudes more compute. So basically, the point of the story here is that if you're using this twice regularized formulation, you get compute, which essentially makes it the regularized problem not more complicated than standard non-robust problem, while solving the robust problem directly seems to be virtually intractable in all but the simplest cases. So the compute is one reason to use twice regularized formulation. Now you can say, well, what about learning? So far, you only told us about planning, and what about learning? So learning is a funny thing in robust MDPs, because in robust MDPs, there is an underlying assumption that you know precisely that is used, that is the concept of twice regularizing. And it's really the same Q learning. Do note that you need to assume that the uncertainty levels are given. And then the difference between Q learning and what we have here is that you need to, your temporal difference operator that you're using, instead of just being what it usually is, which is the first two terms minus the last term, you also have those two regularizers that you need to use. The regularizer for the uncertainty set in the reward, and the regularizer for uncertainty set in the value function. And this is basically it. So use this as your favorite, as your Q function, and that's going to solve the robust optimization problem. And you can do it in also for deep learning based architectures, because this is of course amenable to gradients, with the only exception that you need to calculate the norm of value of VFT. VFT, the value function, computing its norm may appear to be difficult, and indeed it may be difficult, but you can sample a batch of from the replay buffer. You can compute the norm of the batch, use some moving average not to get too far, and if you do that, the V here T from the batch is going to be your estimate. Everything is going to be okay, and now you can ask, well, maybe it's very sensitive to the value of beta, the moving average value. So the answer is no. This is one example that we used. Unless you choose beta to be a very small number, there is no real sensitivity to beta, and you get the distance to the optimal value function is going to be pretty small. So the moral of the story is that instead of solving, if you have some uncertainty in the parameters, you don't need to solve. You don't need to solve the robust problem by other means. You just can solve the twice regularized problem, and everything is going to be fine. In terms of performance, and we look here at the average compute time in three problems: standard problem, Catpor, Acrobot, and Mountain Car. Vanilla, DDQN, and R2 are almost the same in terms of compute. Certainly not orders of magnitude more slower, but then robust Q learning is much smaller in terms of something I wanted to show here. This is performance for Cartpole, Acrobot, and Mountain Car. So high is good. This is a reward. You want to get to high numbers. This is the learning rate, and what we see here is different deviations from the classical problem. So we can change in Cartpole, which can change the force that you're using. So you think you're using a particular force, but you're using a bit less, and the gravity. And what we see here is this performance. So high is good, or light is good, dark is bad, and what is interesting here is to see that when we use a vanilla DDQN, the robust approach and the twice regularized approach, which is really a robust approach, the robust approach has a pretty good performance, which are kind of comparable to R square, to the twice regularized. Maybe twice regularized is a little bit better. Maybe it's a little bit worse. You can see here the numbers. It's a little bit better by and large, but the vanilla approach collapses completely once you deviate from the standard model. And that's, you see here that the colors in the vanilla approach are much darker than in both the robust and the twice regularized. So you get the benefit in the twice regularized of solving robust DQN, and you also get from the performance side, but you get the benefits from the compute side from the as if you were solving DQN. So just to conclude the first part of the story, We have a scalable, robust RL approach, and it has theoretical grounding. We have a robust gradient for general robust MDPs. That's something that we were only able to prove recently. And of course, all extensions to continuous control are really interesting. There are some works on that, and if there are questions at the end, I'll be able to tell you a little bit more. But not much is known about robustness in continuous reinforcement learning. I should mention that there is an interesting connection between you can do either or both. Regularize using the reward the policy, or regularizing using the transitions the product of the value and the policy. And there is one interesting thing that you can do. You can write a value function as an infinite sum, and then once you think about it a bit, then maybe what we're doing here is really a receding horizon regularization. So maybe what we're doing is we regularize the horizon, but in a receding way, so that the future counts for less, and that's something that is left for as an afterthought more than anything else. So with that's the first part of the tale. I want to move to the second part, and then if there are any questions on the first part, now would be a good time.
Professor Manor, can you hear us?
Yeah, I can hear you.
Yeah, so in your algorithm, you had some alpha R and alpha P. So you had made some assumptions about that in terms of the uncertainty. So I wanted to know, are these quantities known, or these are some things we need to estimate?
So the assumption, and that's a major downside of the approach, that those quantities are known. For example, if you're using, say, a Bernstein or some other Hofting type inequality, then the number of samples that you use to construct the model may be something that you would reflect in those alpha uncertainty quantification parameters.
Thank you. I think there are no more questions. So maybe, yeah, just a minute. There's one more question.
Sure.
Hi, sir. I'm Ganesh. So here in R square MDP, are we trying to balance the trade-off between the computational efficiency and robustness through regularization? Is that what we are trying to do?
So that's something that we were saying. There is really no need for a trade-off because if you're using this twice regularized approach, then you get to have your cake and eat it too. So you have both complexity of essentially classical MDP, and you get the robustness that you would get from robust solution. The only downside that it cannot accommodate for every possible uncertainty set. But for the uncertainty set that we presented before, you can in fact have your cake and eat it too.
Okay. 1 second.
Hi.
Just a quick question. So all these results are tied to the rectangular uncertainty sets, or do they extend to the other forms? Like, I don't know, like.
Yeah. So the results are tied. The regularization results are tied to the rectangularity assumption. Recently, there are some results that work with non-rectangular uncertainty set, especially. But it's still, you need to assume something, because the worst case non-rectangular is NP hard. So we're not claiming that P equals NP here. All that we're saying is that you can do, for example, policy gradients for other sets as well, more general sets, but not for the most general ones.
Okay, and how does this theory extend? I mean, in the context of like policy gradients, or even with function approximation, does this extend to those setups? Can I still do some kind of an approximate like actor critic algorithm with regularization?
So the short answer is yes. It extends to, because of the contractive nature. Basically, most of the theory for policy gradients and relates on some local properties, and those are preserved by twice regularized models.
Okay, yeah. So that's all I had. Thanks.
Quick question, Professor Manor. You showed that for some sets of uncertainty terms, you could derive the regularizer correspondingly. Is that?
I couldn't hear the question. I'm sorry. Can you repeat, please?
Hello, check. Hi, can you hear me now?
Yeah, I can hear you.
Okay, sorry. So quickly, so you showed that there was a relationship between uncertainty term to the regularizer. Is that an easy derivation of how do we go from that uncertainty term to the regularizer?
It's a pretty easy derivation. It's something which is like a Fenchel transform. So there is a formal way to do it, and the computation may not always be nice, like we had in the example that I showed you. But formally, you can move from a rectangular and uncertainty set to a regularizer.
Okay, thank you.
Okay, so let me move to the next part of the story, and this part is really when I'm asking for your help. So this is about delay MDP, and the motivation is if you've ever taken a shower where there is a delay between having a hot water and moving the faucet and then getting a hot water, then you know that delays can be pretty painful. So the motivation is really how do we work in models where there is a delay between a latency between decisions and actuations. And I'll describe work about acting in delayed MDPs. And just as background, we'll assume here in the next thing, almost all throughout all of this talk, maybe with the exception of the second to last slide, we assume a fixed delay m. M is known, and there are two ways to think about delay. Whether it's execution delay, so I make a decision now at time t, and this decision really is executed only after m steps. So I think about stopping my car now, but because I'm slow, my car does not react fast enough. It takes 300 milliseconds for the car to stop. So this is the execution delay. On the other hand, there is also potentially observation delay, which is I get to see, I'm now at time t plus m, but I only get to see the state that used to be at time t. Now the two are equivalent. So whether you have execution delay of m or observation delay of m, those are the same thing, because the information that you have is tail. This is the information that you have, which is m steps old. And whether you make the decision at time t or at time t plus m, it does not matter. In both cases, whether it's observation or execution delay, your action is going to be delayed. Why is that a bad thing? So this is a simple example, a toyish example. Here we have two states. The states are S0 and S1. When you're at state S0, you want to choose action A0, that's going to give you a reward of 1. When you're at state S1, you want to choose the other action. And the transition probability is P. So it doesn't matter really what you do. If you start at state S0, then and you have an execution delay of m, then the best thing you can do is you can you can try to estimate the probability it's going to be in one state or the other, and then it's not easy to prove that if m is this is going to be your optimal return, and obviously as p goes to 0.5, or as m becomes very large, then the return is going to go. You have no control over the decision. Or alternatively, if p goes to 1, meaning the problem becomes more or less very small, then the return is going to go to optimality. So the example here is that as the problem becomes more stochastic, or as the delay becomes larger, then you get performance degradation with respect to deterministic or short delay. So how would one approach such a problem? So there is one, a naive approach is to try and do what's known as augmentation. Sometimes it's also called lifting. In augmentation, we take the original state space S, and then we augment it with the action Q. So we look at the current state, and then the action that we had at the last m step. So the action one time before, the action 2 times before, until the action m time before. And we can do it now. You can solve it any way you like. It's an MDP. And then the issue is that from a computation perspective, it becomes quite challenging. So what we see here is that if you use policy iterations, then we have an almost matching upper and lower bounds by giving counter examples, where you'll need at least S a to the power of m iterations, or and that's essentially what you need. And if m is large, then this becomes exponential. And in fact, those are bound on the compute in general. So what we know is that if m is not tiny, so if m is not very small, augmentation, if you augment, you can solve the problem precisely. It's an MDP. Then, while the problem may appear computationally easy, it is in fact exponential in the delay. So the question is if we can do better. So let's think about it. Maybe we don't have to augment the MDP. Maybe we can still do something which is a bit. We can look at instead of looking at stationary deterministic policies in the augmented space, maybe we can do something else. So what we show here is that there exists a non-stationary Markov policy. So basically, the theorem here is that Markov policies are optimal in the sense that for every history-dependent randomized policy, there exists a Markov policy, which gives you a same process distribution. And in fact, there are MDPs for which delayed MDPs for which all stationary policies are suboptimal. So you really need stationary policies in delayed MDPs are not going to solve it. So how do we do it? We look at a sequence of initial action laws. So those are the decision that you make initially, and we look at what we call the delayed value function. This is a delayed value function is for a sequence of decision laws, and this is the expected return that you would get from the last or from starting at time m of this decision laws. And you get here a Bellman type equation. So this is the theorem here, that you get the delayed value function satisfied something that looks like a Bellman equation, but now you're optimizing not on a single decision law, but rather on m decision laws jointly. So that's what's written here. You're optimizing over m laws. And your value function depends on m laws jointly. So that your policy is now a sequence of m consecutive decision policies. And you can show that in fact it suffices. The maximizer is deterministic. So you don't need to look at Markov random policies, but rather it's enough to look at Markov deterministic policies. So what we're saying here that for infinite horizon optimum without a delay, it's stationary deterministic. With a delay, you need infinite horizon optimum is now Markov deterministic. So you need basically to go beyond stationarity. And what we have here is a DQN type algorithm that implements the policy that I had before. What's interesting here is that now we have a delayed environment. We have a forward model that builds our estimate for the future. We have a queue network, and then we have an action queue. So we feed actions to a queue, and then those actions are going to build a forward model to the future. So the way to think about it is that the input to my action choice is going to be my estimate of my non-stationary Markov policy that is going to build something that is going to look m steps into the future. That's my forward model. It builds one of its heads estimates what will happen in m steps, and I choose my queue network so that it's going to feed my action queue for the future. So this might look like a pretty complicated scene, but all in all, what I'm doing is that I'm jointly optimizing m actions together. So, and I reiterate or I solve through my model iterated m times, where m is the queue length. So that's our new algorithm, which we call it delayed queue. Here are some experiments to show you that this is we have three domains: a tabular domain, and then there is a noisy cart pool, and then there is Miss Pac-Man from Atari. Those are not very difficult, perhaps, but also not completely trivial problems. We see m equals f0. This is there is no delay. M equals 5, m equals 15, and m equals 25. And then we have in blue augmented queue. So this is what happens when you take the state space and augment it with the last m actions. So this can become a bit large when we have delayed queue. So delayed queue is our algorithm, and when we have oblivious queue, basically ignore everything that happens. So in m equals 0, basically, of course, augmented queue and oblivious queue are going to be pretty similar up to random fluctuations. Delayed queue should not have any improvement because, well, the problem is delayed. As you start increasing the delay from 5 to 15 to 25, then delayed queue really works much better. Oblivious queue at some point just cannot solve the problem because, well, once the delays become large, then the problem is becoming quite difficult, especially for the noisy cart pool, because the delayed queue simply cannot work. Now, concerning oblivious queue, interestingly, even though it's an MDP and the optimal solution is stationary and deterministic in the oblivious queue world, the state space explodes quite quickly. So oblivious queue sometimes find it's very hard to do anything which is useful, like we see here in the noisy cart pool. It just collapses completely, and its performance is completely random. And we tried it for many domains, and a similar picture appears in most of them. Okay, and that's again we see a graph where on the y-axis we see the episode reward, and on the x-axis we see the delay value, and the colors are the same. Blue is augmented, green is delayed, and red is oblivious. They all start from a delay of 0, where the performance is essentially the same up to some noise, and then as you increase the delay value, the oblivious queue collapses at some point. The augmented queue at some point collapses too, and in most problems, and the delayed queue still has good performance. So let's talk a little bit about the delay. So sometimes we assume so far the delay is fixed and known. So somebody tells me the delay of m decisions, and that's it. Now, sometimes there is an unknown constant delay, and sometimes there is an unobserved random delay process. And maybe there is also sometimes unobserved state-dependent delay. So those are three really interesting cases which we addressed in a paper that appeared last IIClear. And that's I'll share the solution, but basically I have to say that formal results for the above, I don't know how to obtain formal results for the above. And I'm sure that there is a formal relationship with robustness. I just don't know how to formulate it properly. And it's a really interesting research topic. Then let me just share you the solution. So the solution that we had, this is an empirical solution in the paper. I don't know how to prove anything about it. We have a delayed environment, and what we're building here is we're building a forward model. This forward model tries to predict what's going to be the state in the next ZT delay. So there is stochastic delay. If the delay is random and we can track it, then we know that T. If we can estimate it, then we estimate it from data. Then based on our state estimation in time T plus ZT, we do a tree search policy. So we search a little bit into the future, and then we choose the optimal action according to our value function. And this is the action that we're going to choose. It's going to go into the delay environment and so forth. So basically, the point here is that our forward model takes the current state estimate and the action that we get from the delayed environment. So those this is the action buffer from time t to time t plus zt. And we're doing this whole estimation loop, and we get a solution that works well in practice, even though, as I said, we don't know how to prove much about it. So let me recap with the main lessons from both tales. So we get this story that robustness equals, in some sense of the word equal, written here as nothing formal, equals regularizations. And we know that delayed MDPs can be solved effectively without any embedding, so we don't have to exponentiate our state space. And we know that we can solve practically stochastic delays, but we're not really sure how to do that in theory. So the question that I'm left with is, can regularization really solve stochastic delayed MDPs? So either a way to consider delayed MDPs and somehow think about those as regularized versions of another MDP. And then if that's the case, then what's the connection between generalization, delay, and robustness? Robustness seems to be a fairly and delay, especially stochastic delay, seem to be a complementary terms, and both are needed for generalization. If you think about it, if when you think about human motion or any motion which is smooth, it's kind of resilient to small changes in a delay. If I'll ask you to walk around with some weight on your back, I mean, as long as the weight is not too large, you should be able to do it. So, and similarly, if for some reason you have a longer legs or different shoes, and that's going to cause a small delay in your actuation, that's also not going to be a big deal. So somehow, to be able to generalize, we need to be robust to parameters, meaning the weight on our back, but also to delay. And those are two, it seems to be that those are two faces of the same coin. How to make this formal is something I do not know how to do. And last but not least, everything that has to do with continuous time delayed RL-based control, that seems to be a fairly difficult notion in terms of proving things. But that seems to be also fairly important because, as I said, I believe that delay and or robustness to delay and generalization go hand in hand. So with that, I will conclude. Thank you for your time. I think we have time for a question or two.
And we have time for maybe one quick question. So, question from the audience.
So, Professor Manoj, thanks for this wonderful talk. I wanted to ask, in this delayed MDP, when you talk about the state augmentation, why are the augmentation only in terms of actions, and why is there no state? That was not clear to me. And maybe a quick second question, when you say regularization and this robustness, do you have an example where the two are not equal?
Yes, so thanks for the question. So first about the augmented MDP. When you have an augmented MDP, then the actions are the same actions. It's just that whenever you're choosing an action, it's going to go into two places. It's going to affect the state dynamics, and it's going to affect in a way where it gets into the action buffer. So it gets into the action buffer, and then the next state is chosen according to the delayed state and the delayed action. So basically, everything works in terms of the dynamics. It's just that your state space now is exponentially larger in terms of the length of the delay. So that's concerning your question about augmented MDPs. There's nothing wrong with using them as long as the size of your action space or the delay is not very large. Concerning your question about whether there are cases where regularization and robust are not the same, so there are examples where a particular type of regularization does not have a robust counterpart, and vice versa. So there is our robustness measures or robustness formulations that where you cannot. There is no polynomial way to write a regularized formulation. So unless of course P equals NP. So in short, the answer is yes. There are formulations where you cannot move between the two. On the other hand, I do believe that every rectangular robust MDP can be reformulated as a regularized MDP.
Thank you.
Okay, so
thank you.
So thank you, Professor Manor, for that excellent talk. So next up, we have our next speaker, Professor Francis Bach. So Professor Bach is a researcher at INRIA. Well, let me first make sure that Professor Bach can hear me. Okay, great. Can you? Okay. So Professor Bach is a researcher at INRIA, where he's been leading the machine learning team from 2011, which is a part of the computer science department at École Normale Supérieure. He graduated from École Polytechnique in 1997, and he completed his PhD in the computer science department at UC Berkeley in 2005, where he worked with Professor Michael Jordan. He spent 2 years in the mathematical morphology group at École des Mines de Paris. Then he joined the computer vision project team at INRIA, École Supérieure, from 2007 to 2010. Professor Bach's research interests span machine learning, especially in sparse methods, kernel-based learning, neural networks, and large-scale optimization. In 2024, he published the book Learning Theory from First Principles, and he's been the recipient of several prestigious awards. So let me name a few of them. He received the INRIA Young Researcher Prize in 2012, the ICML Test of Time Award in 2014 and 2019, the NeurIPS Test of Time Award in 2021, and the Lagrange Prize in Continuous Optimization in 2018, the Jean-Jacques Moreau Prize in 2019, and he was elected in 2020 at the French Academy of Sciences. Okay, so with that, I'll let Professor Bach take over.
Okay, so can you hear me?
Yes, we can hear you.
Okay, so first I would like to thank you for the generous introduction and for inviting me to that workshop. I wish I could have come back to Bangalore, but it was not possible this time. So can you see my slides?
Yes, we can see the slides.
Yeah. Okay, very good. All right. Okay, yep. So let me start. So what I will talk about today is joint work with Sylvain Bonabel, a colleague from École des Mines, and our recently graduated PhD student, Marc Lambert, who's the driving force behind that work. So what would be the outline for today? So I will talk about reinforcement learning but from a different point of view, from the point of view of model-based control. And as I will try to convey in the next slide, that those problems, at least in the way RL is being used at the moment, those two problems are essentially equivalent. And once we're going to look at the new contribution that we're proposing in this work, which is to add some entropy regularization, which has been known from before. But this new entropy regularization will have some benefits for the solution of the problem. It will create it will have some consequences on the type of policy which we can get, but it will also allow us to use to open the box of variational inference tools, which is a box coming from a toolbox coming from probabilistic modeling, which is heavily used in machine learning, in shallow or deep learning, and the idea is to show that those tools can be used. And all right, so let's go. So first, what is the difference between reinforcement learning and model-based control? Expert in any of those, so I'm learning, and but this is my take on it. So the two frameworks beyond the change of notations, okay, look at the same problem. I have some agent with a state space state X. It's often S in reinforcement learning. And the agent can take some actions or some controls. So I'm going to denote them as U, okay? And often it's A in the context of reinforcement learning. And once you add state X and you take action U, so something will happen. The environment will provide you with the next state. And this can be done in a discrete time, which is very classical in reinforcement learning. But in control, there's often continuous time control problems, and many of the control problems people are faced with in industry or in practice are in fact continuous time. But in this talk, I will mostly focus on the discrete time because it's a bit easier. And so this means that if I am in a discrete time, I need to know the probability of the next state xk plus 1 given my current state xk and the control of my action uk. So this is the environment is modeled by that. And then how do I characterize the performance of my policy of my control is through some reward which you may want to maximize, but I'm going to use the cost which I want to minimize along the trajectory. So there's a sum over the trajectory of a loss given by my state and my control plus the termination cost. Okay, so compared to the classical Markov decision process in reinforcement learning, there's a finite horizon and no discount factor. Those are just like I would say minor differences. Okay, but the goal is really the same. So in model-based control, and so here I'm giving like a somewhat caricatural account on what model-based control is. There's many things in between, but just like to be clear, so in model-based control, most often you assume the model is known. Okay, you have a formula to go from xk uk to sk plus 1. And when you're on continuous time, it's in an ordinary differential equation. If you have some noise, you may add some noise. So this is like here I'm adding additive noise, but you can imagine having any type of noise. So this is model-based control. And then once you know those equations, then it's an optimization problem to find U. And there are various ways of doing it, which I will describe in a moment. Whereas if you do reinforcement learning, the idea that at least this is what is claimed in most papers, is model-free. Okay, so we don't have a precise mathematical model of the dynamics, and the agent evolves in the environment and learn online, okay, to adapt and to get a better policy as you go along. And so this is a nice story about reinforcement learning. But if you look at the vast majority of applications of reinforcement learning, we are not in the situation where an agent evolves in an environment and adapts its policy. We're really in a situation where we are going to learn policies with an infinite access to a simulator of the environment. Okay, this is true for games, this is true for robotics, so this is true for a big portion of applications of reinforcement learning. So now Well, so to me, this is indicating that the problem of reinforcement learning with infinite access to a simulator, to me, is equivalent to model-based control. And the equivalent is in quotes because, of course, we don't have a formal mathematical model of the dynamics, but we have access to infinitely many samples. So if I give you any x and u, I can simulate xk plus 1. So I have access to the model by samples, okay? But within machine learning, having access to distribution through its density or through samples essentially is seen as being equivalent. You have a full access, okay, in a different manner, okay, through samples and not through a formula. But at the end, you know the model because you know the simulator with infinite access. Okay, so that's why I'm going to consider the model-based control situation. Okay, and of course the key, and I will come back to that at the conclusion. The key is really to make sure that algorithms access the model in the correct way. Okay, so today I'm going to access the model through a mathematical formula, but if you want to apply to this simulation-based like control, then we need to do other things, and I will briefly mention it there. All right, so this is the goal will be to do model-based control. All right, so what we want to tackle in this work is to look at random controls. Okay, so we're not going to assume that we're going to, given x current state, we're going to generate the control with a deterministic function. We're going to look at a stochastic policy. And this idea is common in reinforcement learning, in particular in the soft actor critic methods, where this is supposed to enhance exploration. Okay, so in the classical RL framework, when the agent evolves, you want to make sure the agent both exploits its knowledge, but also explore other states which may not be optimal, and having random control is a way to do so. The question we want to tackle in this work is, can we do the same thing for optimal control, and what would be the benefits? So there are several potential benefits. The first one is if you want to have some notion of unpredictable trajectories. Okay, so if you have a deterministic control and a deterministic dynamics, then your path is super smooth. So given the position of your when you state at a given time, you can predict pretty well what the state is going to be next time. And if you want to avoid to be predicted, okay, for various reasons I can let you imagine, then adding an entropy term or adding a randomness would avoid like it being detected. Another I think also interesting application is if you want to use soft controls. Okay, so it's known that in the control domain that often deterministic optimal control, in particular if you're faced with non-smooth dynamics, you can have what is called a bang-bang effect, is that at time k, you're going to take a control, and at time k plus 1, you're going to take a very different control. Okay, and so this means that it's like when you drive, you go very left and very right, and this is not going to be nice for anybody, and not for the passengers of your car, and also for the health of your system. Okay, so you may want to avoid bang-bang effects. Also, non-divergible dynamics can be hard because you cannot take the gradient. So the classical theories of optimal control will not be applicable. And there is a nice array sequence of work trying to make things differentiable by adding randomness. Okay, so there's nice work by the team of Justin Carpentier, and I've done some work with Quentin Berthet, looking at using randomness to do smoothing, and this is essentially the way to do it in the control situation. But the benefit I would like to highlight for today is the fact that by using random control and a proper entropy regularization, this will allow us to open the box of variational inference, okay, which is the classical way to do approximate inference. And this is all the three aspects are important, but this is the one which I will focus on today. So to give you like a concrete example, okay, so this is like an inverted pendulum, okay, and so you want to put the pendulum at the top, okay, up, and so it's unstable, so you need to control to keep it there, and so here the control is on the torque, okay, that you put, and the state is characterized by the angle. And what you can see as time goes along, and you start with an angle of 30 degrees, so around there, and you want to get to 0. And in the red, this is the optimal policy. Okay, quickly you will get to the deterministic policy, you will get there. But after a while, you know exactly where you are. And if you want to preserve some uncertainty, then you will have randomized positions, always around the true value. But then at the end, okay, because you have a big cost of being perfect at the end, then you, at the end, converge, okay? And so this is one example of the effect of adding a lot of entropy regularization, trying to make things like less deterministic. And the goal is to show how can this be done and what are the benefits in terms of computations. All right, so let's look at the formulation. Okay, so I'm going to use like classical, like discrete time control theory. And again, this is a optimal control problem starting from x0. Okay, then I'm going to try to optimize over my controls. Okay, so that I minimize that cost. It's at every time k, I have my state xk, I take the control uk, I get a cost lk, I get some terminal cost. And this, I'm going to choose the controls, but then I'm going to evolve according to that like probabilistic dynamics. And the way I like to see it is through like a Markov chain. Okay, so we do have a Markov chain with x, u, and x. Okay, so given x, you take an action u that depends on x, and then you evolve to x1, which depend on both u0 and x0, and you go along. Okay, so that image of a Markov chain will be quite present today. Right, so this is an optimal control problem. Okay, and this is essentially if you had a discrete state u, this is essentially a Markov adaptation process. All right, so when faced with this, okay, so there is a classical way of solving or having a framework that can solve that optimal control problem, which is dynamic programming, which is essentially value iteration in the reinforcement learning literature, where you're going to, so you want to estimate this value function, okay, so this is a value function starting from state x0, and the way it works, you're going to put yourself at the end, okay, so what if I start at what is the optimal value of x3? If let's say n is equal to 3, then I know that this is the one that's minimizing the terminal cost. And then the way dynamic programming works is by trying to see what if I start from x2, and the beautiful dynamic programming principles say that if you know where you are at x2, whatever happens in the past is irrelevant, and you just have to focus on the future. So you get like a recursion to get like the value function at time state k. Okay, if I know I am at xk, what is the optimal policy in the future? But this is simply looking at one step, trying to find a direct control. When I've started at xk and I end up I start at xk and I end up at xk plus 1 to my dynamics here, I know the optimal cost to go at the future. Okay, and then I just have a minimization problem. Okay, so this is a classical dynamic programming. And so here the key is that although this is a determinist, this is a stochastic problem. Okay, I have an expectation because my future state, given my stated control, is random. The optimal control is a deterministic function of xk. Okay, so the classical property of optimal control. So although I'm stochastic, I have deterministic solution. All right, and so what has been already looked at by various people, in particular like Zibart and colleagues, is to add some entropy penalty. Okay, so why do I call it entropy? Because I take the expectation, okay, over the distribution P of u given x of the log density, and it's exactly the negative entropy. Okay, and so I'm adding a constant time the entropy. So epsilon is a constant, so it's a temperature parameter. So when epsilon is 0, okay, I'm just doing nothing. And as epsilon grows, I'm going to penalize a lot the negative. I'm going to get like uniform controls. Okay? And this was the goal. This was the goal of the paper by those authors, which was to add more randomness, okay, in particular for more exploration. So a few things here is that then if the temperature parameter goes to 0, you go back to where you were. Okay, just it's important because we want to make sure that whatever we do can approximate the true problem when epsilon is small. So for those of you who knows like optimal transport, okay, so in optimal transport, you often add an entropy penalty and you get the Sinkhorn algorithm. And here we do something which is very similar. We add some entropy penalty, okay, that allows us to use algorithms which are more efficient. But you have to think of epsilon as either being very small if your goal is to approximate the true policy, or quite big if you really care in adding some noise and exploring. Okay, and for those of you familiar with optimal transport, in most applications of the Sinkhorn algorithm, when you add a regularization by entropy to the optimal transport cost, the epsilon is not that small. In fact, okay, it works better with an epsilon which is not too small. One key consequence of having this entropy is that now the optimal solution is not a Dirac anymore. Okay, so you get like probability of u given x. So now the difference is that you were replacing a minimization problem over the state, the control u, which was let's say which is like a random, which is like either like a vector or a typical vector, by optimization over something which is much bigger. Okay, so it seemed that we have made the problem a bit harder. So now we have to do optimization in infinite dimensional space of distributions. All right, so this was previous work, and what we are considering is adding a full entropy penalty, not only looking at the conditional entropy, because that red term only characterizes the entropy of u given x. Okay, and what we are adding to have more uncertainty is also the entropy of the state x. Okay, we want to have random control that favors a very diverse state. So we add the blue term there, and now the expectation, okay, is taken over all the dynamics and our control. Okay, and using like classical conditioning, this is just the probability of next state plus control given the current state. Okay, so this makes the state even more diffuse. So this is, if you care about if you care about the having like a very diffuse state, but this allows us to have an exact reformulation of the control problem at the variational problem. Okay, so because once we get the conditional entropy there, the conditional entropy of x given u, we can form the whole entropy of the whole sequence xk uk plus 1 uk plus 1. Because this is the goal, is to get the full entropy of the trajectory. All right, now let's see how we can reformulate this as a variational inference problem. Okay, so I'm going to use the Kullback-Leibler divergence between random vectors. So it's a k between p and r. This is the integral of p log p over r, where p is density of the distribution, r also the density. And the way to write it is an expectation over the left part of the KL of the ratio of the density, so of the Radon-Nikodym derivative of p with respect to r. So here what you see in this KL, you see the integral of p log p, negative entropy, and the integral of P log R, okay, which is the expectation over my state P of log of R, okay? And here, we're going to make a liberal use of the KL. We're going to allow the P, we're going to impose that the P is summing to 1, but the R, we're not going to impose it sum to 1. It's not really important because you can always re-normalize it without any changes for the problem. All right, so let's look at our problem, which we are trying to solve as a very time step. Okay, so this is a dynamic programming recursion. I know VK plus 1, and I want to find VK so that I start from the last time and I go back up to time 0. So this is my problem. This is my penalty, my entropic penalty, which is joint on xk plus 1 n uk, given xk. And the goal is to find the optimal policy. So I'm going to the sequence of a few steps. So first, I'm going to. So here I have an expectation. Okay, I want to formulate this as a KL problem. So I have an expectation of log p over r. So I have the log p here already. Okay, so the first part of the KL is already there. Okay, with some epsilon, and then I need to have expectation of I need to get expectation of log r and get an expectation of the cost function, and I'm going to do something very simple. I'm going to take it by epsilon, and this get the exact same thing. Okay, sorry. So this is very classical when you want to interpret minimization as a probabilistic modeling. You take the log, and then you take the exponential, then you get a probability, or you take exponential minus the problem, you get a probability, and take the log again. This is really like something very classical. And once I have that, now I have my full KL part, I have the entropy part, I have the log thing, okay, both multiplied by epsilon. So I obtain like that the optimal control recursion is in fact a KL minimization, okay, between the density of my states, okay, and some probability which I'm constructing based on the costs, okay. And so here, for those of you who are familiar with the Variational inference, so here what I'm trying to estimate is on the left part of the KL. Okay, so we're really in the classical Variational inference where we want to optimize on the left part of the KL and not on the right part of the KL. Okay, this is a classical mini-field inference. So this means that you can leverage all the techniques from Variational inference, which were like really popular like 20 years ago and are still popular, but most of it has been done like quite long ago. I'm going to reuse many of those. All right, so now we have reformulated the dynamic programming as a minimum KL, and at this point, the key is that I've just played around with math and I did a reformulation. There's nothing has been changed. Okay, I'm still solving the entropy regularized and just formulating as a KL. When epsilon goes to 0, I recover my classical dynamic programming, and so this is the key here now is that this is the same equation there that I had just above, and now I have my KL of the KL of the local KL for the triplet UK xk plus 1 model, okay, which I assume known for this problem, and my control, okay. And the goal is to fit as much as possible the costs which are in fact put as a log probability. And so I have a Markov chain, okay, for my state. Those do not form a Markov chain. They form a trivial Markov chain where there is independence between xk plus 1 and UK xk, and the goal is to fit those two. And here, so there are other, I will mention it later, there are other ways of formulating control through like probabilities, but this one is particularly nice because it's really like I add entropy, okay, and then it exactly a K minimization problem, and I know the approximation which I'm making. When epsilon is 0, I go back to square 1, and when epsilon is large, the effect is to make the state more diffuse. All right, so let's see how we can solve that. And so first, okay, so here the equations do not really matter here. What what if I do the exact dynamic programming recursion? Okay, so if I go back a few slides, if so this was the exact value iteration, essentially, okay? Now, if I add the entropy cost, how can I do the exact, what do I get if I do the exact backward pass? And the exact backward pass ends up being replacing minimization by soft minimization. Okay, so it's a very classical effect of adding entropy penalty. You replace the max by a soft max, okay, log sub x is a classical way of doing the soft max. And this is what you obtain there. Okay, so if you have a very simple like dynamics and cost, those like integrals can be done in closed form. Okay, this is reminiscent of Bayesian inference for probabilistic modeling. You set up the problem using probabilities, and inference is just computing integrals. Okay, and we obtain something similar. The problem here is that computing integrals, okay, exactly is typically not possible. Okay, and we know one instance where this is possible, and this is a important instance of so what is called LQR, the LQR control problem. It's a linear quadratic regulator where the dynamics are linear in x and u. Okay, so this is where we see a strong deviation between optimal control and reverse machine learning. RL is really focusing on discrete state, okay, whereas control is really focusing typically on continuous states. Okay, so this is, of course, you can bridge those two. Okay, to me, a key difference is that the default simple model for RL is MDP, finite state space, and the classical simple model for control is LQR. Okay, so we are more in that side. So if you have LQR, where then you have a linear dynamics, it's linear in x and u, you have a quadratic cost, then what you can show is that, and I will provide examples later, is that you can recover exactly the classical LQR recursions with the backward Riccati equations, but with some extra terms due to the entropy. Okay, so this is really one of the few instances where you can do everything in closed form. Okay, this was possible without entropy, and nicely this is possible as well with entropy. But the key here is that the goal is really not to solve LQR in a complex way. The goal is to go beyond LQR. Okay, and one thing we can do is to try to make the problem a bit harder. Okay, and a classical class of problem in control are called control affine, where the dynamics remains linear in U, but the dependence in X can be more complicated. Okay, so here I put just a constant, just the constant term being dependent in X, but the B also can depend on X, and those class control affine problems are quite common in mechanics, robotics, driving. Okay, often you obtain something of that kind, and our goal in this work is, can we apply those variational inference techniques to those problems which already are difficult. Okay? And so what we're going to do is we have to compute integrals, we have to estimate probabilities, and now we're going to leverage what we know from variational inference in graphical models. Okay, use the exact same tools. And the classical tool in that setup is to use like Gaussian approximation, and it's exactly what we're going to do. All right. And all right, so we have to look at the backward recursion, okay, and this implies like approximating the current state P to estimate the current state P, and there is also a need to find the control. Okay, here the equations do not really matter. The idea is that the dynamic programming recursion requires both estimating integrals and optimizing over distributions. And the key here, because we have reformulated this as a KL problem, is we need to find the current state, estimate the current state P of x, and find the optimal control. And here what we're using is a joint Gaussian approximation. This is a classical tool in the area of probabilistic modeling. You do J approximation. So here, one thing that you should keep in mind is that this is quite close but different from doing a Taylor expansion. Okay, so if I have so often you can see a Taylor expansion around the if you have a density Q, and you do a Taylor expansion around the mode of Q, okay, second order Taylor expansion, you're essentially approximating your density as a Gaussian around the mode of the distribution. Okay, so this has led to numerous applications, like in the context of Kalman filtering. This is extended Kalman filter. What we're doing is not this. Okay, we are modeling things through Gaussians. The density may have a variance which is not like concentrated around the mean, and moreover, we have a cost function to minimize. Okay, so typically, and we have done some earlier work with my co-authors Marc Lambert and Sylvain Bonnabel, showing that you get more stability in those than using a Taylor approximation. The reason being that you still optimize something. Okay, so you know you're going to improve. You approximate, you're going to improve, and there cannot be any form of explosion that sometimes you see if you did Taylor expansion. All right, so now you replace P by its variational approximation, and now you go back to classical modeling. How can I maximize this with respect to Q? The key here is that if you compare left scale to right scale, it's important to do left scale because you take expectation with respect to what is on the left. Okay, so since you approximate these with a simple distribution, Gaussians, all the expectation you can do. Okay, and this is a key in doing efficient variational approximation is to do a left scale variational problem. Okay, and now, okay, here the details do not really matter. This is going to be insightful only if you know well LQR. So we're going to have a joint approximation of the state x and u. And then if I have a joint Gaussian, which can write by blocks because I have x and u, from the blocks I can find the state distribution and the conditional distribution, which is my control. Okay, you see appearing as a notation the gain k. And now the goal is to find those parameters, okay? And if you take the classical case, which we know is going to be exact when you have like linear LQR with Gaussian policies, then everything is closed form, and boom, you're going to find the optimal gain, which is exactly the one that you obtain from LQR theory. And the P is obtained, so the precision matrix of the state is obtained through the backward Riccati equation, which is what you would get for classical LQR. And so the mean is the same as LQR, but what you can show that you add some, you get some entropy with, we get some extra randomness, which is converging to zero if the temperature goes to zero. This is a feature of what we're doing, is that if epsilon is small penalty will go back to no penalty. So this is for LQR. Again, here it's not really useful in the sense that LQR is well known, but the idea is what you can do when you're beyond LQR, okay, and you want to solve those you want to solve something like that. So control the fan problem, okay, how is it possible? And this is what we did. Okay, this is what we did, and we essentially do the exact same thing. We do like a variational Gaussian approximation, now using not around zero, okay, because you have to be more flexible, and then what you can show is that what you need to solve to find this optimal variational parameter is to solve some Riccati equation, but now the dynamics is not constant, okay? So f of x used to be x before, but now you see expectations of your dynamics, okay? So this shows that you're going to look around your current mean to various points to average the dynamics to take into account like not only the current point, but all of the points. Okay, so here, if you check carefully, those equations are a bit like circular, because to estimate parameters of Q, I need expectations under Q. It's a classical thing in variational inference in dynamical systems. You may have some, you need to do a few iterations to be able to estimate Q. And this is, so again, here the equations do not matter. What matters is I've put myself in a position where I can use classical tools from a different field. And that field is variational inference. And what you obtain, so here this is going back to my pendulum. Okay, so this is, so here I'm showing the classical control, deterministic, and then I'm saying what's happening if I add some noise with various noise penalty. Okay, so very small in blue to a bit larger in red. The pendulum angle, so I start from 30 degrees, go back to 0 because I'm successful in my control. The control, this is the torque I need to apply to the problem. So it's high at the beginning to get to the close to the solution. Then it's simply like not too large, just to stabilize the problem. And you see the cumulative gain, so the loss function, okay, it goes up, the negative goes up. And if you add some noise, with small noise, recover what we had before. But as you add more noise, then you're going to get a bigger loss. Okay, so it's a loss here. You get a bigger loss, which is normal because you want to have a more diffuse state, so you're going to prevent optimality. You get a more diffuse loss, but the control do not vary as fast. The pendulum does not vary as fast. Okay, it's just to give you an idea that this can be implemented, and we implemented it on the pendulum. And in terms of trajectories, okay, but you can see that we go from very deterministic trajectories because the noise we are having in the pendulum, the natural noise was quite small, to significantly more noise. But as you convert to the end, since we put a high cost on the final state, we still convert the final state. Okay, so it does what it's supposed to do. All right, so a few points to discuss. So there is like a significant amount of related work which I have not discussed. Okay, you can look at those references or in our paper to get more details. In particular, there was several previous work on using a maximum entropy policy. And I think what we're adding is the KL formulation and the variational inference part. Similarly, there were also like various works looking at trying to bridge optimal control with probabilistic modeling, but they are not as direct as there was, I would say. Okay, so to summarize what we did, so our main idea was to look at adding entropy, negative entropy penalty to our problem, so trying to maximize the entropy of our control and state. So this meant having controls which are now probabilistic in X, and the key was to use to open the box of variational inference, okay, to the problem. Okay, so some outlook. So I think our goal, okay, in this work is trying to bridge the gap between reinforcement learning and control. Okay, so I come more from the learning side, and my co-authors, Marc Lambert and Sylvain Badabel, come more from control, and the idea is to bridge a bit our point of view to problems which are equivalent. Okay, so so what can control bring to RL? I think it can bring a lot, and essentially many of the reinforcement learning applications are being done on continuous problems. Okay, and on those continuous problems, there is like 50 years of theory. Okay, that have like highlighted problems with controllability, observability, or many other concepts in control theory. If RL will not be able to solve the problem without looking directly into those concepts. Okay, it's not. It won't work if there is no adaptation of RL to those concepts. So that's what I need. That we need If you do RL, we need to look at control. So the entry cost is not zero because it's a field on its own. I think it's important. And on the other side, model-based control, which relies a lot on mathematical models, but more and more the models come in various forms, okay, like through samples. More and more, the state space will be in high dimensions, and it's exactly what machine learning is supposed to be good at, okay, to do good predictions or good modeling in high dimensions. And if you want to know more about that, how machine learning is doing well in high dimensions, there is like you can read or buy my book, okay, which is there and which will tell you a lot about how to escape the curse of dimensionality in supervised learning, so nothing with RL, okay. But I do believe that there should be some more interplay between those two fields, but this means learning about the other field, okay. So you cannot do control without knowing about control, and similarly, you cannot do learning without knowing about learning. All right, so in terms of like outlook for our variational ideas, I do think there's a lot of potential. And why? Because first, there is a big toolbox with many algorithms. Okay, in fact, Mark and Silver, Mark and Silver Bonabel have with me have contributed to it. And the key here is that it goes beyond doing Taylor expansions. Okay, so this is really something which I believe strongly in. And the key is that by adding this entropy regularizer, we were able to leverage those tools. So very much, again, like in optimal transport, you add some entropy penalty, and you can use like a sync-on type algorithms. And of course, the key now, once you know how to use variational methods for control, is can you start to estimate a bit more? Estimate the state, okay, like in Kalman filtering, which we have already worked on, and of course, estimate the dynamical system in itself. This is all topics for future work. And on this, I will thank you for your attention and take questions.
So, questions from the audience?
So, hello, Professor Bach. Can you hear me? Can you hear me?
Yes, I can.
Yeah, so the first question is, can you provide some motivation for why one would want to look at this optimal policy with minimizing the maximum entropy? Can you give some motivation for that?
Oh, okay. So the one motivation is like purely computational, as I mentioned. If you add the entropy penalty, you can use variational inference. So very much like optimal transport. It's one motivation. You take epsilon small and not too small to get the computational benefits. But in the context of why would you add some entropy? So let's your vehicle is, and you don't want to be tracked, okay? And so adding the entropy penalty allows you to have to add some randomness to avoid being tracked. Okay, so this is one of the reasons, and the second reason is adding randomness will allow you to make things differentiable. Okay, so this is something which is like whenever you do like control with contacts, okay, then you get a lot of non-differentiability. This is a problem for optimal control, and this has been tackled with various tools. But one very simple tool is to add randomness, and this will essentially allow you at least to use differentiable calculus. Okay, this is the second reason. But the reason the one which I'm more familiar with is really to have for computational benefits.
Okay, maybe a second question. So in this paper, it looked like you are looking at a finite horizon problem. And I wanted to know if you extend it to the infinite horizon problem and try to look at the same question, would things simplify or would it remain as complicated as here?
Oh, you mean if I had like a infinite horizon discounted problem?
Yes.
I would say it's just the same, probably. It's a bit. It's no. Details. Well, it's just the same. many things will change, but the principal concepts would be quite similar. We have not today, but it's a good natural extension. No, you could imagine that the dynamic programming, that you have a recursion that is slowly your variational approximation should converge, as you get more iterations. But this is something to be done. But in the optimal control, it is one deviation between like RL and control. It's like a lot of RL is on the discounted policy thing, and a lot of control is on the finite horizon. And to me personally, many of the problems you may want to look at are not infinite horizon with a discount. Typically they are with a finite horizon, but the ones I'm familiar with. But clearly that's a good question.
Hello. So your initial calculation looked very much like risk-sensitive control, where you minimize expected value of exponential of additive cost. So are there any connections that you have explored?
Okay, thanks for the question. I have to admit I don't know what risk-sensitive control is, and so I assume from the name that you're adding some extra cost. But no, if you could like provide me some references like offline, I'd be happy to have a look. But clearly, I'm not aware of this. So maybe we discuss it in the paper. But really, this is where my expertise ends. But probably so we have tried hard to look at relationship between what we do and other frameworks, but I think I'm not sure we went through risk sensitive control.
The initial calculations are exactly the same. You want to minimize expected value of e raised to something, and that's equivalent to you can convert it to a sort of minimization of f plus entropy.
Okay, good. But if you can send me like offline some reference, I make sure to have a look and to see what the similarities and differences are, because probably they are both. But to me, the key idea is to use this entropy penalty as a way to get computational benefits. And it's quite possible, and that this entropy penalty has been already considered in the same form. So we already mentioned the one where you add like the conditional entropy, the one by Seibert, but there are probably like other formulations. But I have a look. Thanks for your question. Thanks for your comment.
Okay, I'll mail you some references.
Okay, thank you.
Any other questions from the audience?
Hi, Dr. Bach. Thank you for a wonderful talk. You mentioned that the addition of the entropy penalty is useful for the computational, the analytical derivations you do, but surely there's other benefits to that also, right? So we see that in LLMs, they use this hallucination parameter to create more actions out of a large action space, right? So there could be other advantages of adding this entropy value, right?
Yeah, I agree. I think the way this was justified by Seibert, what I have on the slide right now, was really to enhance exploration. So this is what you describe essentially, and in the context of when you know the model, I think I'm not sure this is like really useful to explore. But if you want to really explore because to estimate the policy as you go along, or if you want to explore to provide diversity in your outputs, like in the LLM case, that would be the benefit. No, I think this was one of our motivations to add diversity both to the controls but also to the inputs. So in the LLM case, that will mean not only having diversity in the next token prediction, but having diversity in the whole sequence. That would be the difference like between this and the slide and this one. And this one. So that term makes sure that you really add the maximal amount of uncertainty. But again, this is one way of seeing it. The other way is that this allows us to formulate it as a KL problem, minimizing KL between my state plus control and the cost function.
Thank you.
Okay, so let's thank Professor Bach once again for a wonderful talk.
Okay, thank you.
Okay, so thank you, and I think we'll have a coffee break right now before we get back for the final talk. Thank you.
Okay, bye-bye and enjoy the rest of the day.
So, welcome back, everyone. Welcome back, everyone, for the last talk of the day. It's my great pleasure to introduce Professor Vivek Borkar. Professor Borkar was an institute chair professor at the Department of Electrical Engineering in the Indian Institute of Technology in Mumbai. He obtained a PhD degree in electrical engineering and computer science from the University of California in Berkeley in 1980. He has held various positions at the IIFA Center, Bangalore, the Indian Institute of Science in Bangalore, the Tata Institute of Fundamental Research in Mumbai. He's a fellow of the Indian Academy of Sciences, the Indian National Science Academy, the National Academy of Sciences of India, the Indian National Academy of Engineers, Institute of Electrical and Electronic Engineers, and the American Mathematical Society. He has received the Shanti Swarup Bhatnagar Award, the Homi Bhabha and the J.C. Bose Fellowships, the P.C. Mahalanobis Medal, and the TWAS Award in Engineering. And he has been an invited speaker to the International Congress of Mathematics, Madrid, in 2006. So with that, we're very excited to hear about your talk, Professor Borkar.
Thank you, and thank the organizers for inviting me. So this talk I gave this Sunday to a mixed audience, because of which one problem is that there's this 1A, 1B, 1C are kind of tutorials for the uninitiated. So going through them in any detail would be like taking Bisibede Bhat to Bangalore. So I'll do a short job of it. Except perhaps the stochastic approximation, I need somewhat more detail. Okay, so let's start with background reinforcement learning. So you already know that it's basically machine learning for dynamical systems. Specifically, I will consider Markov decision process, both finite state and action. And the idea is to control them based on state and cost or reward observations. That also they can be either online, that means you are actually controlling a real system, or offline, just run a simulation or some toy model elsewhere. So in offline, you have more freedom. Nothing that you can experiment with can generally cause any major disaster, but online you are more restricted. And this last line is put in red because it's kind of the way I think of RL algorithms. It's a cross between classical iterative schemes for MDPs and stochastic approximation, and I'll explain why I say so very soon. So MDP, anyway, this go through quickly. So it's also called controlled Markov chains. So it's a state process xn in a finite state space, control process un in a finite action space, and the dynamics that the probability that next state xn plus 1 equal to j, given entire path till n, just depends on the current state and current control, and that's specified with this function small p of j given xn un. So that I call that the controlled transition probability function or controlled transition probability kernel. Later on, I'll use a similar symbol for something else. So given a cost function C, which depends on current state and control, you want to, this is the simplest cost function, cost functional called finite horizon cost. You want to minimize expected value of the total cost you pay till time capital T. And then the standard approach is dynamic programming principle, which you have heard enough of. So in words, I like this verbal description. Minimum expected cost to go at time n is minimum of sum of two terms, cost at stage m, the immediate cost plus minimum expected cost to go from the next state, that is m plus 1. So just translate it into math. So let me define vi comma t as a minimum cost to go at time t from state I. Okay, so that's just that. The same thing, expectation of a sum from small t to the terminal time, conditioned on xt equal to I. So it's a function of current time and current state. Then whatever this verbal description I gave of dynamic programming principle, you just translate into math, it becomes that vi comma t is minimum over u of ci comma u plus conditional expectation of vj t plus 1 given I comma u. There is sum over j pj given iu. Vj comma t plus 1, and there's a terminal condition vi comma capital T is hi. There's the terminal cost. There's no, I don't put any control argument in h because the whole thing ends there. There's no future after that. So this can be solved by backward induction. You know what v is at time capital T. So you plug in t, small t equal to capital T and solve this equation, and sorry, small t plus 1 equal to capital T, this second line will give you the vi comma t for t equal to capital T minus 1, and you keep repeating that till you come at initial time. And the important thing is that the minimizing u, so there's this min u, min over u of some entity there. Then minimizing u is the optimal choice at that state and that time. So if the, I mean, of course, the minimizer depends on I and t, so I call that v, small v of I comma t. Then the claim is that u sub m of equal given by v of xm comma m is the optimal choice at time m. And it's easy to see that it will be a Markov chain, though potentially time inhomogeneous, because I have allowed time dependence in V. Then the other cost criteria, the discounted cost criterion is a popular one, so it's common in anything involving money, because inventory control and whatever, finance, etc., because alpha is typically 1 divided by 1 plus interest rate in many of these applications. So alpha is something between 0 and 1, and it sort of discounts the money spent tomorrow as opposed to money spent today, which is reasonable. And then the dynamic programming equation, you're just using the same philosophy, same intuition. You write it this way: Vi is minimum over u of Ciu plus the alpha times one step conditional expectation of V at next step. So here I have not put Vi comma t because the infinite future looks the same regardless of when you are at I. So when you are in I, since you are looking at infinite future, assuming the environment does not change, it's not going to depend on t. So that simplifies things a bit. The thing is that it's because it's infinite horizon, you cannot do backward recursion. So but it's of the form f of v equal to v. Basically, if you are right hand side, I write this as a vector equation v1, v2, dot, 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 make it a column vector. Then I have the vector v on the left hand side, and on the right hand side, there's some function f of v. And this f turns out to be a contraction with respect to a suitable norm. So by contraction mapping principle, it is a unique solution. And then the minimizer, small v of I, is the stationary, is called a stationary control policy because it doesn't depend on time, and it's optimal and leads to a time homogeneous Markov chain. Now this is the criterion I'm going to use most of my talk. It's a long run average cost. And the dynamic programming equation is what I wrote there. It's not easy to derive. I mean, it's not hard if you know enough, but for a beginner, it's not obvious. And this, what you do is you look at, let's go back. So this, for discount factor alpha, I call the value function V alpha of I. Then look at V alpha of I minus V alpha of I naught for some fixed I naught. And let the discount factor go to 1. That means you are not discounting in the limit. You can show that this converges and satisfy any limit point of this will satisfy. Actually, it will converge and it will satisfy that above equation. So it's a kind of this dynamic programming equation is arrived at by a limiting argument. And there are two unknowns. The V is an unknown, the value function, and beta is also an unknown. But you can easily show that. I mean, it's not hard to show that beta is actually the optimal cost. So it gets uniquely specified, but V is not uniquely specified. So if it's irreducible, the chain under suitable irreducibility assumption, V is unique up to an additive constant. So if I add some constant C to each of Vi, the equation doesn't change. Okay, so Vi plus C will be minimum over U, Ciu minus beta plus some over J of Pj given Iu, Vj plus C. Okay, it's easy to see. It's just same quantity added on both sides. So it's definitely not unique with respect to scalar addition of a scalar, but one can show that that's the only source of non-uniqueness. So it's unique up to an additive scalar. And the minimizer gives an optimal control, which leads to a time homogeneous Markov chain. And now the algorithm. So I have written these algorithms for the average cost only. So this is basically value iteration, which is a kind of, you have seen value iteration for discounted cost probably. So what you do is start with a guess for V, call it V0, and just keep doing this iteration. The difference from discounted cost is that there is no discount factor. So in discounted cost, before the last term, the conditional expression, you would have had an alpha. That's not there. And in addition, you are subtracting this Vn of I naught. That is because it's no longer, see, this if I drop, okay, let's go back. This equation is also of the form V equal to Fv, but F is not a contraction. So if you just blindly iterate it, suppose the beta is not there, if I don't subtract beta, it in general won't converge. So this V and I naught is some offset you subtract off to keep the iterates bounded. And then you can show that Vn will converge to that particular solution for which Vi naught is beta. See, V is unique only up to an additive scalar. So if I fix its value at some point, then it becomes unique. So if I am subtracting V and I naught, you get a unique, converge to the unique solution for which the I naught component of V is beta. And the other choices, you can replace some general FVN for, it's not any old FVN. It has to satisfy some conditions. In particular, minimum over I of xi, max over I of xi, or average of xi are also legitimate. Basically, f applied to the constant vector of 1 has to be 1, and f applied to x plus c times constant vector of 1 has to be fx plus c. So these are the requirements. And so here the algorithm will converge to whatever I chose as Fe being equal to beta. So once I fix a minimum at beta or maximum of beta or average at beta, it's again a unique solution. So which solution it converges to depends on the offset which is subtract. And Vi naught is the simple choice because you just pick up one value and plug in. But it has the computationally it's somewhat inconvenient because when you are iterating, some changes in V and I naught propagate through the state space very slowly. For example, it's a very large, like queuing. It's a large state space with only, you move from one node to only some neighboring nodes. Because something you disturb at one node, it will propagate very slowly. But whereas the min, max, average are better, but then you have to compute all of that. You need the information about the entire vector. So there are trade-offs. You can cook up some other in-between combinations also as potential V. So this is, so as I said, the RL algorithms are going to be some kind of clones of this iterative algorithm. So whatever I say about this value iteration, policy iteration, etc. applies there as well. But I generally for writing whatever proofs, etc. V and I naught is simple. Though in practice it may be quite slow. So policy iteration, you iterate in the policy space, you start with a guess for the optimal policy and then keep iterating this two steps alternatively. So I fix the policy and solve the dynamic programming. So suppose at time n my policy is small v of n. I just plug in small v n now, you control as small v n of I, then that makes it just an uncontrolled Markov. I have frozen the control. So the dynamic programming equation is basically a linear equation. You just solve this linear system by some linear system solver. And then 2b just says that having computed that v sub n, you pick the next guess for the optimal policy by minimizing that. And alternate between the two. One can show actually that each time there's a strict improvement in Vn. And it converges in, if we are finite state, finite action, it will converge in finitely many iterations, but they can be exponentially large in, I think Francis Bach gave some, I think mod s times mod a raised to n plus 1 or something. So they can be pretty bad, and there's a lot of research on how to beat down the, tweak this algorithm to, you cannot make it sub-exponential, so people try to reduce the exponent. One of my colleagues in IIT, Shivram Kalyana Krishnan, I think. Yeah, Kalyana Krishnan. He is heavily into this. Okay, so let me talk more about this I need a lot more. So there's a stochastic approximation with Markov noise. So the classical Robbins-Monroe scheme, which goes back to 1951, is xn plus 1 is xn equal to an times hxn plus mn plus 1. There's no, that y is extra. So they were interested in the problem of finding zeros of a nonlinear function h. So they want to solve hx equal to 0 given noisy measurements of x. So they came up with this clever scheme, xn plus 1 is xn plus n times hxn plus noise. And the clever thing was, I think there are other bullets on the next page, but the first bullet is the important innovation that they had this step size, slowly decreasing step size n, which sums to infinity, but its squares are square summable. So it goes to 0, but slowly. What I have extra is this yn plus 1, that's called a Markov noise, that came much later in 70s. So Mn is the sort of classical noise. It's a martingale difference noise. It just says that conditional expression of Mn plus 1 given all you know till time n is 0. That means it's uncorrelated with anything known till n. You can also take IID 0 mean, but it's more general, kind of uncorrelated 0 mean instead of IID. I mean, it doesn't have to be identically distributed, but simply uncorrelated sequence. And Yn is the Markov noise in this. This is critical for most RL applications. It's actually a modulated Markov chain. So I won't need its full generality, but regardless, let me define it this way. So probability that Yn plus 1 is in some set A, given the entire path till n depends only on Yn. Okay, but the transition probability is subscripted by xn. So the current iterate modulates the transition probability. So if it has a unique stationary distribution mu sub x, then under reasonable conditions, so this is the key result I want to use. So let me emphasize this. I will be using this all the time. So it tracks this this differential equation y dot t equal to mu sub yt dz h of yt comma z. So if z takes values in finite set, then it will be just sum over I of mu sub yt of I h yt comma I. So you see what you are seeing is the right hand side is simply that hx averaged out over the stationary distribution of Markov chain. Okay. So if p sub x is independent of x, which is what I will have, then pi sub yt is just the fixed stationary distribution pi of the, okay, I'm assuming irreducibility, etc. Otherwise it gets more complicated. So I'm assuming that the small p, the transition probability of y is irreducible, and pi is the unique stationary distribution of p. And as I said that, yeah, okay, so this is the main claim which one uses. If the differential equation has isolated equilibria or isolated attractors in general, then it will converge to a stable equilibrium or stable attractor almost surely under very reasonable conditions on noise. And this intuition is easy to give. So if you consider, say, multiple equilibria, and there may be some unstable saddle points, and so say take stochastic gradient descent. There are local minima, there are stable equilibria, local maxima or points of inflection, if any, and saddle points are unstable equilibria. So what is true is that assuming the sufficient smoothness, etc., if you you take an equilibrium and linearize h around that equilibrium, okay. So look at the Jacobian matrix. So linearize h around that equilibrium. It will have some positive. Typically, it will have some positive and negative eigenvalues. And let's assume that either sorry, I shouldn't say positive or negative. Either right half plane or left eigenvalues can be complex. So they're either in right half plane or left half plane. On imaginary axis is a complicated problem which I'm going to avoid. So that then for each, so from linear system theory, you know that the ones in left half plane correspond to stable directions and the ones on the right correspond to unstable directions. So locally the trajectories look like there's some nice manifolds, stable manifolds. So if you are on that, you converge there. If you are on the unstable manifold, you move away. But if you are anywhere else, you will come closer and then move away. So the important thing is that unless you are exactly on the stable manifold, you won't converge there. So if your noise is sort of adequate in all directions, you get kicked out often enough from the stable manifold that you won't converge. So that's an advantage of noise here. It will always converge to a stable equilibrium. But you cannot say which stable equilibrium. There's always a positive probability for every stable equilibrium. That is also a known fact. So you cannot expect convergence to global equilibrium for SGD unless you go for simulated annealing or something. Okay, so this is another thing I'll need a lot. So there are two time scales. You can have multiple time scales in stochastic approximation. So I'm iterating the xn comma yn, but I've split the computation in two parts. So there's one part where I'm using step size an, the other where I'm using bn. Both so I satisfy the Robbins-Monroe conditions. But I assume that bn by n go to 0. So what's happening is that the second yn is moving very slowly because bn is asymptotically negligible compared to an. So relative to the xn, yn is moving more and more slowly. So that induces some interesting behavior. So there's also third time scale. The capital Yn is that Markov chain running on the natural time scale, which is n equal to 0, 1, 2. So there are 3 time scales here. The natural time scale is your clock, n equal to 0, 1, 2, 3. And then in the algorithm, there are 2 time scales. One is, if I, actually maybe I should, maybe backtrack a bit. So I just said glibly that this, it tracks this ordinary differential equation. And the reason is that you can think of this as a noisy Euler scheme for the noisy discretization of the differential equation. If the, let's say, capital Yn plus 1 is not there, then it's simply a discretization of the differential equation with the slowly decreasing step size and additional noise. So that's why it tracks the differential equation. And what helps is that this condition, some n square being finite, ensures that n goes to 0 asymptotically. So the discretization error goes to 0. So it becomes better and better approximation with time. And also, if suppose Mn plus 1 is IID0 mean, or M is a bounded variance, doesn't matter, martingale difference, then sum of Mn plus 1 is a convergent sequence that follows from something called martingale convergence theorem. So tail of, it's a convergent sequence, so the tail from n onwards, which is noise added from n onwards, is also going to 0 almost surely. So both errors due to discretization and noise become smaller and smaller with time. So it tracks the ODE better and better. So asymptotically, you have to actually use the approximation argument on a moving window. And you can prove that it will track the asymptotic behavior of the differential equation. So here what happens is that you have the 3 time scales, and the idea is that each time scale is faster than the next. So the 2 algorithms are, so for example, my natural time scale is just the clock, n equal to 1, 2, 3. Suppose I take n as of the order of 1 by n and bn of the order of 1 by n log n, okay? Then, did I define? Yeah, I defined this. So the fast algorithmic time scale is the time 0 is 0, then tau 1 is, I'm looking at an and bn at time steps because I'm pretending that it's a discretization of the ODE. So tau 0 is 0, tau 1 is A0, tau 2 is A0 plus A1 and so on, and similarly for bn. So you just add the step sizes till time n. Then for this choice, an is 1 by n and bn 1 by n log n, you get tau n growing as roughly logarithmically and kappa n growing as log n. So you can see that the growth rates are, they become diverge relative to each other asymptotically. And the important observation is that each time scale sees the slower ones as quasi-static, in the sense that you can analyze one time scale by treating anything slower as frozen in time and anything faster as quasi-equilibrated, in the sense that you just average out with respect to this. Or if it's convergent, you take its limit and plug it in, or if it goes to some stationary distribution, average out with respect to it. Okay. So one good analogy is if you are walking slowly on a sidewalk on a major highway, say, when you look at the vehicles, you are not looking at an individual car, right? It's just some big blob moving very fast. And the person in the car, for him, you are more or less static. So it is that effect which helps you analyze them individually. So you analyze one at a time, average out over the faster time scale, freeze the slower time scale, and just analyze this. So anyway, I'll be doing that for RL. So Q learning is this algorithm. Anyway, I first define the Q values. Q value is always what you minimize in the dynamic programming equation. The dynamic programming equation is V of I equal to min over U of blah blah. That entire blah blah you call Q I comma U. Okay. So just as you had Q values for the discounted cost, I have this Q values for average cost, and I have chosen this again has a unique solution only up to additive scalar. So if I freeze it at I naught comma U naught to some fixed value beta, and then it will satisfy this QDP dynamic programming equation. This is easy to it just follows from by plugging in Q in place of V in the V equation. Okay, so this is what you get. Oh, I thought I had corrected this. The min U outside is not there. There's only min W inside. There's some. So yeah, remove the min U outside the summation, because that's the crucial part. in the V dynamic programming equation for V, the min was outside the average. Now min is inside the average. So once the average is outside, you can do stochastic approximation. So you no, it's a non-expansive, it's not a contraction. Yeah, so I can write this relative Q value iteration, which is just like relative value iteration, except that the min is inside the thing. And as I said, the recipe for writing the RL algorithm is I have a conditional expectation, get rid of it, and plug in an actual evaluation. So what I do is remove the conditional expectation, and in min W of Qn j comma W, I replace j by the next state, which is xn plus 1. Because this conditional distribution is exactly P j given I comma U. So at time n, when I have state I and control U, okay, so this, if I just did that and kept iterating, it would be like a correlated random walk, won't be very stable. So you have to make it incremental. So I take a convex combination of the previous iterates, so Qn plus 1 IU is 1 minus n times Qn IU plus n times this indicator is because at each time you see only one I comma U. So at time n, I have xn is I and un is u. So indicator xn equal to I, un equal to u is 1. If xn equal to I and un equal to u, 0 otherwise. So what that means is at time n, I am updating only I youth component. Oh, I think that indicator should have also multiplied another error. That first n should have also been multiplied by the indicator. Okay, so but then I collect together all terms involving n, then I get this clean. This is the Q-learning algorithm for average cost. Okay. And Qn converges to a solution of the Q dynamic programming equation, where to the solution corresponding to Qn I naught U naught equal to beta. And this can be proved using the ODE method. This was in my paper with Abunadi and Bersikas. And okay, so this I already said, the QDP equation instead of DP equation moves the conditional average outside the minimization, which facilitates stochastic approximation by you just replace the conditional expectation by an actual evaluation and make the iteration incremental. Okay, and stochastic approximation basically does the averaging for you. The best way of seeing this is you can write if you have independent IID random variables with mean mu, and you define Sn to be sum of IID random variable xn, say with mean mu, write Sn as sum I equal to 1 to n xi, and consider Sn by n, you know that Sn by n goes to mu, almost sure by law of large numbers. You can write down Sn iteratively as Sn plus 1, so let's Xn be Sn by n. Then Xn plus 1 is Xn plus 1 by n plus 1 times mu minus Sn. It becomes a stochastic approximation. So in some sense, you can think of stochastic approximation by pushing the idea of strong law of large numbers to various classes of depending random variables. So the second algorithm I will consider is actor critic. So these are two time scale schemes. So this, of course, I am looking at only tabular versions. No, this has to be done differently. This is harder. So the way proof goes is that I'll replace Qn I naught U naught by beta. Call that value iteration. I think I forget what I think relative value iteration or whatever. That ODE it will be Q dot times some TQ minus beta minus Q, where T is some operator. That can be shown to converge, but because the solution is non-unique, it converges to a point depending on where it starts. Then the hard part is to show that this ODE, which will be Q dot equal to TQ minus Q I naught U naught times vector of 1s minus Q. Each trajectory of this can be obtained from the trajectory of the previous one by some kind of space-time warping. So if you plug in beta there, you analyze that as a non-expansive map. But it's non-expansive, it has a whole straight line of solutions. It will converge to one of them depending on where you start. But once you do this, it freezes the I naught U naught component. You have to just exploit the relation between the two.
Thank you.
Yes, so actor critic algorithm is similar. The critic part, the guy who evaluates the thing, is just doing value iteration. Here, it's not a problematic as in Q learning because the policy update is on a slow time scale. So you treat it as frozen. So it's a constant policy value iteration. It's a linear stochastic approach, effectively linear. So you can analyze it more very easily. And I have not written the policy updates because policy updates there are multiple choices in this. So actually, this was I don't know if I give the reference anywhere. Yeah, this was analyzed. The tabular form was done in my paper with the former student Vijay Mohan Rao Konda, and there are 3 different policy update schemes given there. And what you see now as policy gradient is also actually it's a different iterate, but it also fits the same model. To calculate the policy gradient, you need to run a value iteration. So essentially the same paradigm. So it's a 2 time scale. The slow policy is fixed because it's on a slower time scale, and so this is easy. The value iteration is easy to analyze, and the policy. Okay, so what? Because we're treating policy as constant, what V does is Vn track. Suppose I call V sub pi the value corresponding to fixed policy pi. Then what Vn does is Vn minus V pi n goes to 0. It tracks the value corresponding to the slowly varying policy pi. So when you analyze the iteration for pi, you replace the Vn there by V pi n, so it becomes self-contained equation. You can analyze on its own. It's clear? Yeah, I have written it here. Okay. The slow actor iterate does the optimization taking as input the value function of the current policy, which is well approximated by the fast iteration. So it's so Vn minus V by n goes to 0. So the actor iterate will depend on Vn, but you can replace that Vn by V pi n modulo another negligible error. So this is just so Q learning and Q learning is like value iteration, actor critical is like policy iteration, and with Shalab and one of his students, we also flipped the the step sizes in actor critic and got something called critic actor, which again mimics value iteration. And there are these policy gradients. So I'm just listing everything that is around. There are for fixed policy here, this TD lambda, LSP lambda, etc. And yeah, so LSP lambda is seems to be not that popular. This was Bertseka's idea, and it has more computation per iterate, but if you consider just the number of steps, it's much faster than TD lambda. Okay, so this is the main thing. So the thing is that when you write RL algorithms, you take Xn as the state, and this is sort of implicit assumption that it's a Markov chain. And there can be other issues like it's large dimensional, continuous valued, etc. So this, anyway, I'm not going to touch. But the thing is that, is it a Markov chain? If not, what happens? And that's the thing I want to analyze. Okay. So this based on these two, the later part, if there's time, I will talk about something in this paper with Chandak, and there are multiple students from ID. And the second part is yet to be written. So I'm assuming, so I'll justify this later. I assume that I started at time minus infinity and look at the stationary state processes, stationary control process. And the zeta n and zeta bar n are two history processes. In zeta n, I take xm up to the state up to time n, but control up to time m minus 1. And that's because you choose control un at time n. It's not something you already know. So I distinguish between zeta n and zeta bar n, where you also include zeta n. And then either of xi n or xi bar n is an S infinity valued, so it should be S cross U infinity valued control Markov chain. See, if you have any process, you consider the entire past as one state, it's trivially a Markov chain. Okay, it's nothing profound is being said here. The main important thing is that I assume that this one step conditional probability that xn plus 1 is in A, given the entire past, is a time independent function P. And okay, so this is weak. I mean, with this, it doesn't have to be a stationary process, but I am also assuming that it's a stationary process. And I want to consider this average cost control. And I would allow it to depend on the next state also. That doesn't matter much actually. And so this, the reason this is convenient is because it's easy. It's anyway you are looking at asymptotic behavior. So any string till time, a finite string doesn't matter. So eventually I'll be soon talking about asymptotic behavior only. So thinking initial time as minus infinity is all right. So without loss of generality, I'll specialize this further, but right away we can assume that the control un is just some fixed function of some randomized control. The phi, the control un in B, with the probability of control un in B given the history, is some phi of B given the history. So I assume there is some fixed function, and the standard MDP argument tell you that for long run average this class suffices. So this far nothing much has been done. It just looks complicated, but just do whatever you always do for a usual Markov chains for this infinite string. S infinity cross U, S cross U infinity too, yeah. So under phi now U is a function of phi, so xn becomes an S infinity valued Markov chain with stationary transition probabilities, and we'll consider the stationary ergodic regime. That means ergodicity just to ensure there's a stationary fixed unique stationary distribution. Otherwise, more generally, you can always decompose any stationary law is a convex. The set of all stationary laws is a convex set whose extreme points are ergodic, so you can look at them individually. So, okay, so this is this third para is the key statement. I'm assuming everything stationary and etc. because I'm looking only at asymptotic behavior and 2 time scales, and that the algorithms are on slower time scale, either single time scale algorithm or double time scale. So for algorithms, the processor always on a natural time scale, so you always treat them as stationary because this control will be fixed. Okay, so yes, so you are going to average with the stationary distribution of this infinite Markov chain. That's the idea. So let pi be the marginal distribution. That means the distribution of xn I assume to be some fixed pi. That's because I assumed it's stationary and ergodic. Okay. And then I play a trick. So define the control transition kernel Q. Q of A given xn comma un is expected value of P of A given the enter past conditioned on xn comma un. Okay. So this will be by construction a transition probability kernel, and then it's easy to check that pi is the stationary distribution for this also. Okay. Actually, maybe I have I have that. I have the proof, but it's not particularly profound, so I'll skip that. So pi is the stationary distribution for if I. So I treat this. Okay, I think I skipped something.
What is pi here?
Yeah, I think I skipped the definition. This slash var phi I have to. So this un, okay. Okay, let's think of it this way. Suppose I take conditional expectation of q of A given xn un given xn. Then the conditional of un given xn I call phi, var phi. Okay. So that this kernel q A given xn un, I can also view it as q bar of the A given x phi x, where phi x is a randomized stationary control. Okay, I have skipped some key definitions, looks like. It's okay, nowhere to write, I guess. But so define phi du, say phi, say phi of B given x is a conditional expectation of, sorry, let me call it a var phi. Var phi of B given x is the conditional expectation of phi B given un and xn equal to x given xn equal to x. I average out un as well. So so one can verify through just manipulation of conditional averages that pi is a stationary distribution for Q bar as well. So let X tilde n denote the stationary Markov chain with control transition kernel Q controlled by this control U tilde n, which is the stationary randomized control, where you choose the next control according to the transition probability phi, so var phi given the current state X tilde n. Or the equivalently with the uncontrolled transition kernel Q bar. And then by induction, you can check that the laws of the triplets xn, un, xn plus 1 and x tilde n, u tilde n, x tilde n plus 1 are same for all n. I cannot say anything about anything more than this. See, law of xn, un and law of x tilde, u tilde n, I have basically matched them by hand. And the next one depends on the same transition probability, essentially. I mean, in first case, it's not a, okay, let me put it this way. X tilde n, u tilde n, xn, un are laws which are matched by hand because I constructed the Markov chain so that the marginals remain the same. And the transition conditional probability of x tilde n plus 1 given x tilde n, u tilde n is the transition probability of xn plus 1 given x up to n, u up to n conditional average conditionally again over xn, un. Okay, so just by construction, they are the same. So this is the big claim that when we treat xn as a straight process of a Markov chain in an RL algorithm, you are actually doing RL. The algorithm is actually viewing it as x tilde n. So it works with some equivalent Markov chain. There's a catch in this. I'll come to that later. So outline of the proof, just to use stochastic approximation with Markov noise. So I have basically repeated some things here. So this zeta n plays the role of the Markov noise yn. And yeah, that basically just plug in the stochastic approximation theory for this big Markov chain zeta n, and you see that the stationary pi will be stationary marginal for both of them. And the claim is, yeah, this is the catch. It's not obvious that it does not mean that the algorithm, because it's running the algorithm, it's actually looks at an equivalent Markov chain. Equivalent in the sense that the laws of the triplets being matched. That does not imply that what the optimum it gets for that particular thing, whatever it learns, is optimal for the original, because there's the averaging over. Basically, what you have done is looked at the conditional probability of next state given the entire past, which will be the function of the entire past, averaged out over, you just fix x and un and average out the entire past. That also changes depending on un. So it just tells you that it solves it learns Q value for some Markov chain, but that doesn't mean it's optimal. Yeah, you'll need that here. So, you do. No, I mean, you need that for the Markov chain, which is true because pi is fully supported by ergodicity. No, see, the Q-learning algorithm will treat this as a Markov chain algorithm, and if you find Q value and minimize it, you will get U as a function of state of x tilde, not x. So it's seeing only one finite state. That's what I'm saying is that need not be optimal for the original infinite chain. So you can plug in all RL algorithms are on a slower time scale, so you can plug in any of them and conclude this, but there's another catch. So I'm assuming that the policy is updated incrementally, but incrementally in the sense it's slower than the natural time scale, but that's not always the case. So suppose you do epsilon greedy for Q learning, because you want adequate exploration at each time. This is a standard epsilon greedy. At each time n with probability 1 minus epsilon, you pick the minimizer, one of the minimizers, and with probability epsilon, you pick something uniformly. So if the minimizers are non-unique, the choice of controls is also on the natural time scale. So this argument will flounder. So what you should do is, I mean, you can sort of salvage it by iterating in the space of probability measures on the control space, and then adding some small convexifying penalty to make sure that the minimizer is unique and moves smoothly. And the error, okay, so this now I fall back on the previous paper. So in the previous paper, this connection with an equivalent Markov chain was not made. But what we did was to get a kind of concentration bound of the, not the standard variety. The standard concentration bound are for finite time behavior. That from time 0 you start and get some concentration bound of what's happening at time n. What I've been looking for in a few things, including I think this should have been Chandak 2024, is the first author. So is some kind of a bound. So I have this ODE limit. So I look from some time n naught, I look at the ODE trajectory, consider an epsilon tube around it, and get a bound on the probability that you remain within that epsilon tube forever. Okay, so it's for all time concentration bound from time n naught onwards. And how big n naught you need depends basically on how small step sizes you choose. Smaller the better. So that has this concentration bound gets bound on that error in terms of sum of many terms, and so you can identify those. So there's one corresponding to approximation error, the steps, this is discretization error, because you are not doing the ODE, you are doing discretization. Then there's another error due to the martingale noise, which we bound using one of these martingale concentration inequalities. And that's from before, but there's an extra error term due to non-Markovianity. And that depends on the difference between your Q value guess at time n, conditional expectation of that given the entire past minus conditional expectation given only x and un. That's precisely as you expect the error. So I was saying something which is obvious. So basically, if whatever you are picking as xn is a good enough representation of the past. So for example, you may be working with, typically you are working with features evaluated as states. So they are not Markov. Okay. So if they are sufficiently representative, the better they capture all the past information or even the current information, the better for you. So they have to serve as what's called sufficient statistics in statistics. So they have to, so in statistics, sufficient statistics, when you are predicting y in terms of x, if conditional distribution of y given x can be written as conditional distribution of y given some phi of x, then the phi x is a sufficient statistic. For example, for Gaussian, jointly Gaussian random variables, mean and variance or mean vector and covariance matrix are sufficient. So generally you don't have such finitely many sufficient things, but then one looks for approximate sufficient statistics. So what your features do should be, they should behave like approximate sufficient statistics. So this is what we are trying to advocate in that particular paper. So your features should also be dynamic. So you have another neural network or something, you feed your current observation. I mean, it's not Markov, so it's just xn, I call it observation, and current control, and the current value of your feature jn, and have this size so that the jns are the features. At time n, you use jns. And the difference is that you are just taking a fixed function of the state space or the whatever this, I call them static features, you are partitioning it. Okay, finitely many, suppose features take finitely many values. That's the case we have considered. It just partitions the whole thing into finitely many blocks. So each time you look at one of the partitions. If you have the dynamic picture, what you are doing is each time you are looking at a partition, but these partitions get redefined with each iterate, and I mean, but they're invariant under that dynamics. You get the same partition again and again, but you are looking at a different piece of the partition each time. So this is, yeah, so I have sort of taken the, see, I have this statement I make by analogy, and I have emphasized the word pure analogy because it's only an analogy. The main reason I'm playing it safe because I don't completely understand what that internal model principle is. Professor Vidyasagar will know it inside out. Something in deterministic control, but I like the statement. It says that when you are, I think, I don't know who it goes to, I think Bruce Francis and I think that group, right? You can correct me. That when you are doing adaptive control, you should have a, so internal model principle says that a controller should have a model of the system you are going to adopt. So I feel that instead of having say static map from your observation control to the next decision, have a dynamic recursion, so a recurrent neural network or something that's more natural for RL. That's the, and of course we propose something based on autoencoder and did some numerical simulations, etc. And the difference, okay, so this is the thing. So SN is the current current output of this gadget. ON is the observation. UN is the current control. ON is the new observation. So the idea is to we call it in autoencoder there's encoder and decoder. So we just use that word encoder, but we call the second box predictor. So you cook up so the dynamics, that psi which I cooked up, the Jn plus 1 equal to psi of whatever. So that's the first box that gives me next SN. And then with that and control, I predict the next observation. And then compare that observation with the actual ON plus 1. And use that error to tune the parameters. That was the idea. So the summary, okay, it's the last slide probably, or last but one. So there are infinitely many typos as well, looks like. Yeah, so the main purpose was to analyze the effect of treating a non-Markovian scenario as Markovian. And this is kind of a mimic, this word mimicking I borrowed from some other, there's some pure, in probability theory, there's something in diffusions, etc. There's Ito process, there's something called mimics. If you can reproduce the one-dimensional marginals of a non-Markov Ito process by a diffusion, Markov diffusion, it's called a mimicking problem. And then I have made a case for dynamic features, and a particular architecture is proposed. And with that, I conclude with a quotation from one of the Beatles. I don't know if current generation has heard of this guy.
Questions from the audience?
So maybe one question. So when you talk about these dynamic features, so you are using these features for approximating what is not clear. Can you elaborate a bit?
No, basically it's we are approximating the dynamics by another dynamics with smaller state space.
I see. And then the next question was, with this, approximating this non-Markovian with Markovian, I mean, are there some conditions where we can show that this leads to near optimal policies? Maybe if you look at switched Markovian systems where you are just having two MDPs and you keep jumping betwing them or something.
See, the gut feeling is that if, for example, it's a rapidly mixing process, like stationary processes, this condition, well-defined notion of rapidly mixing, then that means what we are seeing now doesn't depend on the very long past. So such situations, I think it will do better.
I see. Thank you.
How much the memory, how fast the memory decays.
Other questions? Okay, so let's thank Professor Borkar again for that wonderful talk. Small token of appreciation.
Yeah, that's the point. Yeah.
Yes. Okay. So we are done for the day today. So we will rejoin at 9 a.m. tomorrow. Okay, so we will have Professor Bertsekas speaking at 9 a.m. So that's an online talk from 9 to 9:30. I request that we all assemble maybe by 8:45 so that we can start on time. Okay, thank you.